Logarithmic functions are the inverse function of the exponential function. Now, exponential functions can be written in log form, and log form can be written in exponential form. So there's a difference between function and form, and I'm going to talk about form right now. So we're going to start with the log function, which is y equals log base a of x. And before I get started, I'm going to just change this a to the word base, and I'm going to change the x to the word argument. So the argument is your input. That's what you're going to put in to your function. And then your output is the y value. So this is your input, and y is your output. And that's why we have the x in the position of the argument, because it's the input. Now this is a log function, and it is a log form. So I'm going to write that here. This is a log function in log form. And it's a little challenging to see what the inputs do, what the rule is, what that function rule is, when it's in log form. The more we practice log form, the easier it is to kind of work with it. But many times we need to put it into exponential form to really see what we're supposed to be computing. So y equals log base a of x is the same. It's the same exact thing. It's the same as. That's very, very important. It's not an inverse of these two things that I'm writing are completely equivalent. It's the same thing as saying a raised to the y power equals x. This is also, on the right-hand side, a log function, but this time it's in exponential form. An exponential form is a little bit easier, like I said, for us to work with because we know how exponents work. The difference between a raised to the y power equals x and a to the x power equals y is that one is a log function and the other one is an exponential function. So when your input into your exponential is a y, then you have a log function. When your input into the exponential is an x, then you have an exponential function. Both of these are in exponential form. The one above, a raised to the y power, is a log function in exponential form, and a raised to the x power is an exponential function in exponential form. So we're just going to practice writing the different forms because honestly, the crux of logarithmic functions and working with logarithmic equations is all about being able to go from exponential form to log form and log form to exponential form. So let's practice. Our first example is going to be 8 raised to the second power. We want to write this exponential equation, which is 64, in log form. So we're going to write log base argument. Now, when I write that, notice how the word base is a subscript, and log, argument, and exponent are all on the same line. These are all on the same line. So the base is the base of your exponential form. The argument is going to be what that base raised to the exponent is equal to. And then, of course, your exponent, hopefully that's kind of self-explanatory, is the exponent of the base. And likewise, when I'm writing this the opposite way, I can use the same idea. Base raised to the exponent equals the argument. Here, And sometimes I say the exponent is the answer. I mean, actually, sometimes I say the argument is the answer when I'm going the opposite way. So if I say that, argument, answer, I try to say argument, but sometimes I slip and say answer. So we're going to write log base 8 of 64 equals 2. So hopefully your eyes and your brain will start to see 8 raised to the second power equals 64. Okay, let's try another one. 9 raised to the 3/2 power equals 27. So again, we have a base of 9, we have an exponent of 3/2, and we have an argument of 27. So this is going to be log base 9 of 27. Now sometimes I will write the argument in parentheses. I'm going to try to do that as a better habit from this point forward, equals the exponent of 3/2. And then I can check and say 9 raised to the 3/2 is equal to 27, which is what we've written right here, which is a true statement. The square root of 9 is 3. 3 cubed is 27. Here's another example, this time with a base e. E raised to the 0 power is 1. We know that that's true. Log base e of 1 is equal to 0. We know that log base e is called the natural log. So I rewrite that as ln. So the natural log of 1 is equal to 0. And that's our final answer. You will see me, though, write log base e many times because I've trained my brain to see that base and then raise it to the exponent equals the argument. Now we're going to evaluate without using a calculator. So we're going to use this property to evaluate without using a calculator. So we've got log base 2 of 1/8 equals something. So what does log base 2 of 1/8 equal? I'm going to start the more you know your exponents, the more you can go straight to the answer. But until you know your exponents, 2 raised to some power is equal to 1/8. Now you can name that some power whatever you want. Like you can, that power, you can name it an X, you can name it an A, you can put whatever you want in there. But what do we have to raise 2 to the power of to get 1/8? And that's where we say, well, 2 cubed is 8, so 2 to the -3 would be 1/8. So let's try another. Here we've got log base 10 of 10, and we want to evaluate that. So I'm thinking 10 raised to what power is equal to 10? And that's where you can perhaps just look at this and say it's equal to 1. Now, sometimes we can't calculate or evaluate without using a calculator because sometimes our numbers just don't turn out to be integers. Our exponents don't always turn out to be perfect, and they don't always turn out to be rational. They tend to be some decimal value that is irrational. So here's an example of that. If I have log base 10 of 4/5, that means 10 to some power is 4/5. And 4/5 is the same thing as 0.8. Now keep in mind that log base 10 is the same as just writing the word log, and that log base e is the same thing as writing ln. So one is a common log. That's the one on the left. Our common log is base 10, and our natural log is log base e. So we're going to put this into our calculator, and I'm going to actually show you how to put this into your calculator without having to use a change of base formula. Okay, so I'm going to go to my camera real quick here. I'm going to show you my calculator. So we want to enter in log base 10 of 4/5. So we're going to hit the log button. So we've got this log button right here, log, and then in parentheses, I'm going to put 4 divided by 5. And you can use your fraction bar if you like to use a fraction bar. I'm used to using the division bar, so that's how we enter log of 4/5. And that's how we ensure that all of the argument, using parentheses, all of the argument is kept together, 4 divided by 5. So that's our value for log base 10 of 4/5. Now for natural log of, let's write that one down. So we'll write down this is approximately negative 0.097. Just getting used to our calculator. And then the next one is going to be the natural log of the square root of 5, and then plus 1. So notice how there's no parentheses here. This means, and that's why I like to use parentheses, because then it's very clear what the argument is. But here it is extremely clear as well. Unless the square root of 5 plus 1 is in parentheses, the only argument is the square root of 5. So you have to just take the natural log of the square root of 5 first. And then whatever that value is, you're going to add 1 to it. So you'll add 1. So I'm going to go over to my calculator. I'm going to show you the different potential errors that you might put in. I'll start with the correct natural log, and then I'm going to put in parentheses square root of 5 and parentheses. And then I press enter. There's a syntax error because I put that parenthesis on the inside of the radical, and I needed to put it on the outside. And I press enter. So the portion of just natural log of the square root of 5 is 0.805-ish. And then I'm going to add 1 to that, and I get 1.805. Now, if I put the natural log of the square root of 5, and then I come outside and I put plus 1, my calculator is going to give me the correct answer as well. However, if the argument was the natural log of the square root of 5 plus 1, where the argument is all of the square root of 5 plus 1, we're going to get a very different answer, which is wrong. So make sure you are being able to identify the argument. That's the big part. So that's why you're going to see me use my calculator, my parentheses a lot, because I like to just see that on paper. I believe it was 0.805. So 0.805 plus 1 is 1.805. And hopefully that's a good explanation of how to identify what goes in the argument and what does not. And I think we have a couple more pages. Yep, we have a couple more pages. We're going to get to the graphing. Before we get to the graphing, just want to put in some basic properties of logarithms. Just remind you of some basic properties. If I have log base A, any base, now bases, I'm going to come back here. The base, I'm going to use some interesting color here. The base has to be greater than 0. You cannot have a negative base. It has to be greater than 0. Your argument has to be greater than 0. It cannot equal 0. The base cannot equal 1. The argument can equal 1. The base cannot equal 1. So the base has to be positive but not 1. The argument has to be positive. 0 is not allowed in either position. And then your output, right here, your output, can be any real number. Any real number, positive, negative, because that's your exponent. So if we look over here, your exponent can be any real number. Your argument has to be positive. Your base has to be positive. Zeros are not allowed because they are not considered positive. So base and argument must be positive. The base cannot equal 1 because that would be silly. Then I'd have 1 raised to any power would equal 1. And it would not be a function. It would just be a constant. So it wouldn't have an input and an output. It's just a constant value. So the base cannot equal 1. So back over here, we've got log base A of 1 equals, and this one's pretty easy to remember, the base raised to what power equals 1? Well, any base raised to the 0 power, other than 0 being raised to the 0 power, is equal to 1. And then another property, log base A of A raised to what power is itself? A raised to the first power is itself. So log base A of A is equal to 1. So whenever the base and the argument are equal, that value of the logarithm will equal 1. Then we have log base A of A raised to the x power. That's going to equal x. So A raised to the x power equals A to the x. A to the x power equals A to the x. Makes sense. And then A raised to the log base A of x is also equal to x. And I can prove this one by writing it in log form, log base A. So I'm going to take this base of A and put it here, of x. So here, of x equals the exponent of log base A of x. So there you go, right there, an identity. So this proves that property right there. So these are 4 really good properties. I would, if you're not remembering them very quickly, you can make index cards. So you've got on the first side the expression on the left, and then on the back side of the index card you've got the value on the right. So left-hand side, right-hand side, front of the index card, back of the index card. So a few times using those index cards can make a huge difference. And then if you have log base A of x equals log base A of y, then the arguments must be equal. So if you have log base A of x, one logarithm equals another logarithm with the same base, then the arguments must be equal. Then x must equal y. So I'm going to go through these pretty quickly. Our first example, solve for x, log base 2 of x equals log base 2 of 3. We're going to look up here and try and figure out which property. We've got property 1, property 2, 3, 4, and 5. Log base 2 of x equals log base 2 of 3. We want to solve for x. That's going to be property 5. Because they have the same base and it's one logarithm equals one logarithm, we can go straight to the arguments being equal. So x has to equal 3. Next, log base 4 of 4 equals x. That's going to be property. Let's see, we have the base and the argument being the same value. Base argument equals the same value. That's going to be property 2. So x is going to equal 1. And then this says simplify, because all it is an expression. Log base 5 of 5 raised to the x power is equal to, actually there is no equal to. We just want to simplify that. So we're going to come up here to our properties and say it's not property 1 because that's an equation where we have a 1 in the argument. It's not property 2 because the base and the argument are, well, it could be. It could be, but This argument doesn't have an exponent, and this argument does have an exponent. So I'm going to look for the property that matches this one, and it's property 3. So log base a of a raised to the x power is equal to x. So this is the same thing as saying x. Same thing as saying x. So log base 5 of 5 to the x is the same thing as saying x. And then we've got another example, 7 raised to the log base 7 of 14. And what does that equal? That's going to be property, it looks like that is property 4 right here. So the key here is I've got an A and I've got an A. So I need to make sure that the base and the base, that both bases are equal, and they are. And then I've got a logarithm, so it looks almost exactly the same. So this x is a 14. So since a raised to the log base a of x is equal to x, 7 raised to the log base 7 of 14 is equal to 14. Some simple applications of those 5 properties of logarithms.